So, at the end of the last lecture, I showed this result showing how rainfall will change on account of increase in carbon dioxide during the last 20 years of this century as compared to the last 20 years of the last century. Okay. During the period April to September, and you see a very clear signal of increase in the tropical region of Africa, India, China and equatorial Pacific, but decline in the mid latitudes of America, Amazon region, Middle East and North Africa, South Africa and also Australia. So, this is a very, very interesting result, but I pointed out that we should be careful about this may not happen in the next 20 years or 30 years, because the changes imposed by increase in carbon dioxide will occur along with natural decadal variation of rainfall due to the energy exchange between the ocean and the atmosphere. So, natural decadal variability will show some changes. So, these predictions of this model can only be trusted if you look at data at 2081 to 2100. Looking at this picture, you cannot say what will happen between 2031 and 2050, you cannot. So, for that Georgi and B came up with a quantity called the time of emergence. The time of emergence of the impact of increasing CO2 will be different parts of the world, and as far as India is concerned, his results show around 2050 is when we can be confident that some of these predictions of the climate model may come out true. Before that, the variations in our climate will be both a combination of impact of CO2 and the natural decadal climate variability. That is why it is not wise to look at each extreme event that is occurring in India or other countries and say that is due to climate change, because climate change is occurring in a context of natural climate variation. Right now both are playing a role and one cannot say one is more important than the other. Okay. So, this fact is sometimes forgotten by our media and also by many NGOs, non-governmental organizations, which are trying to create awareness about climate change. They also tend to sometimes exaggerate some of the predictions of the climate models. We need to be careful. So, I want you, those of you who are taking the course, to be clearly aware that our ability to predict the impact of increasing carbon dioxide cannot be trusted in the next 20 years, because there is natural climate variation on a decadal scale which has the same amplitude as the prediction by the climate model about the impact of increasing CO2. Okay. So, you have to keep that in mind. Now, the other important issue with climate models is that in a country like India, where we have Western Ghats and which are small mountains, and the big mountain, the Himalayas and Tibet. Okay. Most models whose resolution is typically 0.5 degree, 0.5 degree, do not resolve some of these mountains correctly. Okay. And some of the models are even 100 kilometer resolution, and they will not get the Western Ghats accurately. For example, in the Western Ghats, all of you know, in Kerala there is a gap called the Palghat gap, where the Western Ghats is not there and the air rushes through those gaps, and those areas are very suitable for windmills. So, the most of the windmills in Tamil Nadu are located in that Palghat gap, but the model will not be able to take care of the impact of Poulgard gap if the model is 100 by 100 kilometers. Okay. Only when you go to 50 by 50 or 20 by 20 or 4 by 4 kilometers, then you will be able to get the Poulgard gap. So, if you want to trust the prediction of climate models about rainfall over Western Ghats or Himalayas, you need to be careful. You should choose a model which has a high resolution. This I will take up when I talk about monsoons a little later. So, here you can see that a model that was developed by Japan called NICAM, okay, the model simulation is shown on the right. Resolution of the model is 7 kilometer by 7 kilometers. It is very high resolution. Okay. Left hand side is observation from a satellite called TRMM, Tropical Rainfall Measurement Mission. You see that this model simulation of the rainfall over Western Ghats as well as the Burmese mountains is very good. Okay. But that requires 7 kilometers. Most of the models used today to predict climate change do not have this resolution. So, the IPCC results which have been put out over the last 20 years, they are with models whose resolutions are typically 50 by 50 or 100 by 100 kilometers. They cannot be trusted to get the rainfall correctly over the Himalayas or the Western Ghats. But you can see that once you get a high resolution model going, its simulation is very realistic. So, this shows that there is promise that in the next 10 to 20 years, as the computers become more powerful and have a higher speed, the model simulation of rainfall near the mountains like Western Ghats and Himalayas will improve substantially. Okay. Now, to highlight that, I am showing a simulation made more than 20 years ago in Japan. This is the MRI model of the Japanese forecasting center, and so one of our students who did his PhD thesis from our center in IISc went there for his postdoctoral research, and he simulated the 10-year mean rainfall over India using this model with the resolution of 20 kilometers with the observation of the India Met Department, and you can see the model did extremely well. Okay. It correctly simulates the high rainfall over Western Ghats as well as high rainfalls in Himachal. I am sorry, the high rainfall over Uttarakhand here, that is the red lines here, and the high rainfall in northeast India, which has lots of mountains, and the spatial pattern of rainfall over the Indo-Gangetic plain, and the rainfall shadow in Karnataka to the east of the Western Ghats. So, I would say this model with a 20 kilometer resolution, the work done almost 20 years ago, is quite good. Okay. Now, not only the model simulates the June, July, August, September rainfall, okay, summer monsoon, it also simulates the winter monsoon correctly. That also you can see the pattern is quite good. So, I would say a 20 kilometer model can be trusted to produce the spatial pattern of Indian rainfall quite well. But I want you to remember that model like CIMIP 5, CIMIP 6 do not have the resolution. They are typically 50 kilometer, 100 kilometers. So, those models cannot be trusted totally to get the spatial pattern of rainfall over areas like India in where the mountains play an important role. Okay. Now, to highlight this even better, I am showing you the 20-year average rainfall June, July, August, September as observed in this left hand side figure and as simulated by the 20 kilometer resolution model, and it is quite good. It gets the gradient very accurately, and it shows clearly the need for a 20 kilometer resolution model to correctly forecast rainfall over the Western Ghats in Kerala. Okay. So, this is a very important requirement. If you want to predict the future climate change over Kerala, you have to have a model with a resolution of 20 kilometers. Now, what does this model predict about the future? Okay. Now, in this model, the future means the last 20 years of this century compared to the previous, compared to 81 to 2000. And this model says that most of India rainfall will go up. Okay. We are confident. All this hatch line shows we are confident. But the same model shows rainfall will decline over Kerala. Okay. And in some parts of northeast India. Now, this was never ever shown by any other model, because the other models have resolution typically 50 or 100 kilometers, and they didn't get the orography correctly over Western Ghats, so they didn't show this decline. This decline is occurring because the jet which comes over India during the monsoon has shifted due to climate change. When the shift occurs, the rainfall increases over the Western Ghats in Maharashtra, but declines over Kerala. So, this is a unique prediction of this model because of its high resolution. Okay. The model also shows that the extreme rainfall above 40 millimeter per day, which causes heavy flooding in many urban areas of India, that is going to go up in this region, central India, will go down over Kerala. And this prediction, a logarithmic scale of the occurrence of rainfall versus daily maximum rainfall, shows in the future there will be more extreme rainfall than the present. Okay. So, this is a cause for concern, because extreme rainfall do a lot of damage both to agriculture and to many human dwellings. And the fact that rainfall above 90 millimeters per day will increase in the future climate compared to present climate here in blue shows that we need to adapt to the possibility of much more extreme rainfall in the future on account of climate change. Now, this also, whatever I showed you is also seen in the actual observation, that there is a decline in extreme rainfall over Kerala in the period 1998 to 2007 compared to a period 1961 to 70. There has been decline in extreme rainfall in the Western Ghats and some increase over West Bengal, Bihar and parts of Bangladesh. But the challenge we have is that most models used right now do not have the resolution to predict rainfall on a scale that people need. When we talk about impact of climate change, you must remember that people are talking about impact in their area, not global mean. Global mean models are doing fine, okay? But that is only to check the models are running properly. What we need is rainfall increase over Bangalore or New York or London at a scale of say 20 by 20 kilometers. But that is not easy because models do not have that resolution. So, what people have done, this very popular method is called statistical downscaling. It is a method in which you take the output of the model, which is at a much coarse resolution, and statistically related to what may happen on a higher resolution. Now, this paper by Shashikant and others, published in Journal of Hydrology 10 years ago, warns you that there is a large uncertainty in the circulation patterns in the models that are used for downscaling. So, we cannot totally trust the prediction of climate models on a regional scale. So, keep that in mind, because I find many people look at the output from these models and make dire predictions about what may happen in the future, but you have to be careful about statistical downscaling, because it is not that accurate. Okay? So, this must be kept in mind. Now, one of the reasons why these models are not doing well over India is because of the cold bias of the ocean. We discussed cold bias about 20 minutes ago, and a good example is here. In the Arabian Sea, black is the observed seasonal cycle of temperature. Okay? And all the green various colors here are various models, and the model mean is the black total line. Okay? And what you see is that most models in the month of April, May, June predict a temperature which is around 2 degrees lower than the observed, which is a serious problem, and the same models ultimately produce a too low rainfall. So, you can clearly see that the cold bias of the Arabian Sea will have adverse impact on the rainfall over India. So, models have to try very hard to improve their ability to forecast the Arabian Sea temperature accurately if they want to get the rainfall over India correctly. Okay? So, this is a work of Levine and highlighted by the Met Office, and you can see that this is a serious issue. So, what is the bias in the ice water path? It is shown here for both CMIP 3 and CMIP 5, and you can see that model ice water path is too high at higher latitude, and but still too low in the lower latitude. So, whether you take CMIP 5 or CMIP 3 does not matter. Models have bias, they produce too little ice, and so one cannot trust these models completely. Now, here is a graph showing the vertical structure of ice fraction. Okay. The solid black is the observed value, and various colors are the models. And you can see that approximately half the models predict too high a ice fraction, while and you can do nothing much about it, because we saw ice fraction is a serious issue in climate models. Now, how about rainfall? In this slide, we are showing in black is observed rainfall rate, and what the model shows is that the common climate models show rainfall reasonably well at low rainfall rates, but at a high rainfall rate they are very inadequate. So, this problem is not been resolved as to why models are not able to capture the heavy rainfall regimes that is seen in observation. For example, okay, you don't worry about that part, we will look at this a little bit later, why the models are doing poorly at high rainfall rates. So, here is pentile rainfall from June to September in many models along with observation, and you can see that the prediction of most models for the rainfall over Indus, Ganga, Brahmaputra and Mekong is actually high compared to what is observed. So, we need to improve the models in order to get this discharge accurately. Now, India Met Department has been running the CFS V2 at a high resolution to get a better model. Okay. Now, what are the models saying? Now, on the top is the model simulation compared to India Met Department. Model showing two high clouds, okay, and you can see that this is two models mentioned here. One is the regular CFS V2, which has a resolution of 38 kilometers, and the other is WRF, also rainfall model. Now, let us look at Sahel rainfall. Now, the Sahel rainfall is very important because in the African Sahel region shown there by hatched line, rainfall declined dramatically in the 1960s, and which led to a major drought in Mali, Niger, Chad and Sudan. And so, there was a lot of debate about what caused this decrease, but now in the 80s the rainfall is revived. So, models are trying to see how they can simulate the decline in rainfall in the 60s and the increase in the 80s. Now, one of the models discussed by Giannini shows that the model observation is not bad over Sahel. Sahel is this region, this eastward oriented region over Africa, and which has been having drought. So, the model shows that the rainfall will normalize, declines over 50s to 80s, and after 80s inclines. Now, here is a picture showing from satellite how, because of the increase in rainfall during the period 1982 to 2003, the greenery in Africa has increased. There is a change in normalized difference in vegetation, NDVI. So, this is a satellite based inference or amount of greenery on the surface of the earth as obtained from satellite data. The advanced very high resolution radiometer AVHRR, it shows all the way from 15 west to 25 east. In the period 1982 to 2003, there has been an increase in NDVI, that means it has become more green. So, we need to understand what caused the decrease in rainfall from 1960 to 1980 in Sahel, and what caused the increase in rainfall in the period 1982 to 2003. This is an important puzzle. Okay. Now, this was modeled by Zeng et al. In 1999, okay, and they compared the observation, which is the black lines here, and the simulation for the period 1980 to 99 is shown in these white dotted lines. Okay. And what do you see? What you see is that if you had only an ocean atmospheric model, okay, then the model does not show any decline. This gray line is the model simulation, black is the observation. Okay. So, model does not reproduce the decline that is seen in the observation. Sorry, here the black lines are each year and the solid line is the what you might call the decadal variation. Okay. And you can see that the coupled atmospheric ocean model does not capture the decline that well. There is some indication, not very good. But if you go to atmospheric ocean model with land vegetation feedback, there is slight improvement. Okay. But if you go to ocean and land, but you add vegetation, dynamic vegetation in the model, okay, then it correctly simulates the change. Okay. So, this is the point that is made by this paper, that you want to capture the decadal variation in Sahel. You need to have not only a good atmospheric ocean model, you need a good land model, albedo of the land, plus a dynamic vegetation where greenery will change in response to rainfall. So, this is a very important result obtained by Zeng et al., showing the importance of land vegetation dynamically interacting with the rainfall. Okay. So, this AOLV correctly simulates what is observed by rainfall data. Okay. Now, now many models are correctly simulating, this is for 50 to 2000 period, they are correctly simulating the decline in that period as observed and as simulated. So, things are improving in the models. Okay. And here we are showing region climate model simulation correctly reproducing the mean rainfall during 2003, the 5-year average observed and model simulated. So, the models are improving quite rapidly. Now, why are the models sometimes not doing well is brought out by this comparison of the net radiation at the top of the atmosphere. Okay. This is observed from satellite IRBE. Okay. So, there is negative over Sahara and positive over 10 to 15 north. UK Met Office correctly reproduces this pattern, although it is a little too negative over Sahara, but the MPI, that is the Hamburg model, does not have the negative sign here. So, it will tend to produce too high rainfall over Africa because it does not reproduce the net radiant top of the atmosphere, which is the energy input into the monsoon model. So, if you look at the aerosol, role of the aerosol, which we discussed earlier in our lectures, annual mean visible aerosol overall depth from 2001 to 2005 using MODIS, okay, and the model output simplify from 2005 the difference. Okay. So, what we see is models are not getting, the differences are very large and negative, okay, over India and Southern Africa, is too positive over Europe. So, model is producing too high aerosol over Europe and too low aerosol over India and South Africa and South America. Okay. So, this shows that aerosol in the models are having some difficulty. This is partly because accurate data was not available before year 2000. Okay. Only after satellites came, we had an accurate estimate of the aerosol over many regions of the world, especially the tropical regions. And so, the aerosols were not correctly modeled in these simulations. So, I want you to remember that when you look at model simulation, there is a cascade of uncertainty. First is scenario, we have to predict how CO2 aerosol will change in the next 50 years. And we see models of uncertainty due to clouds and aerosols. And if we take the model and downscale it to a high resolution using a statistical scheme, there is uncertainty. And finally, we use it to predict floods in a hydrological model, there is other uncertainty. So, there is a cascade of uncertainty. So, we need to be very careful in trying to believe the output of models without proper validation. Okay? That is the message that I want to give at the end of this lecture. We will continue this issue in the next lecture. As we look at model output from now to 100 years from now, where is the uncertainty large? Is it the initial condition, is it the emissions, or it is the model? So, this slide I will talk in the beginning of the next lecture. Okay? Thank you.